we're solving linear equations. There were two main methods. The first one is the substitution method. And the second one, I like the name addition method, but you'll also see it's called the elimination method sometimes as well. So last time we basically covered the substitution. In that method, don't you want one of the equations to be written as y equals something or x equals something, and then you go and substitute it. In the addition method, you kind of want, eventually, you want this kind of pattern. You want the same number of y's plus and minus, or the same number of x's plus or minus. Now, if they're already set up like this, it's good to go, but most of the time, you're going to have to change one or both these two equations to get it into that form. So this is the form it needs to be for the addition method to work. And that's kind of where we left off last time. So I'm going to do a normal kind of no frills version of that. And then I'll show you some adaptations that you have to do, because sometimes the equations are not written in a very useful way, for want of a better word. So I'm just scanning through to see if I can find one that's nothing particularly special. Right, this one here is question 10, or at least it's like question 10. So it's going to be 4x, take away 3y equals 9. And then it's going to be 3x plus 2y equals 11. And I like to call them equation 1 and 2. It just makes my descriptions easier. Now, when I look at these two equations, I know that it's not ready for the addition method, because if I try and add these, they don't kill each other off. And I try and add these, they don't kill each other off. So I look to see which one I want to get rid of. Technically speaking, it really doesn't matter. I can decide to get rid of the x's, and or I can decide to get rid of the y's. As I say, it doesn't matter. Excuse me while I open up the windows to see your faces. Something's not right. Okay. Try some here. There we go, that's better. Right, I can see you now. So if things go wonky, I'll at least be able to tell from your faces. What we got here then is you can get rid of the x's or get rid of the y's. I try, sometimes anyway, I try to pick one that I think's less work. What do you want me to do? Get rid of the x's or get rid of the y's? It's really just a choice. It's not important. You got to tell me, x's or y's? What do you want rid of?
Y's.
Okay. Did you choose the y's because at least one of those plus and minus, so it's a little bit less work? Or did you just randomly pick?
Yes.
Yes to the first or
I
the
picked
second?
It. To the first.
Okay, so it was this. So what you're going to do here is you're going to get both of these have to change. And essentially you multiply this guy by 2 and you multiply this guy by 3. So let's see what the new equation looks like. If you double all these guys, you get that. And if you multiply everybody here by 3, you get that. So that's essentially our new equations, and I'll draw my little wall to separate them. Now these are ready for the addition method, and that's what we do, we add. And these get you 17x. These essentially kill each other off. And that's 30, 40, 51. And so to find x, I just divide both sides by 17. And we've got half the answer, half the solution. Came out really nice. It's no guarantee, but if you ever get a nice number here, it's a good sign that things are going well. If this ends up being 17 145ths, you might be a bit worried about, adding or subtracting. You might have screwed up somewhere. Now, once you have got one half of the solution, don't you then substitute? x equals 3 into, does it matter which one of these two equations here I substitute the x equals 3 in? No. Anybody got a particular preference, or will I just pick one? Do you want equation 1 or equation 2?
Equation 1.
Oh, darn it in space. I wanted 2, but doesn't mean you're wrong. It's just I wanted to do that one. So there it is. So it's going to be 8 lots of 3. And so it's going to be 24. If you subtract 24 from both sides, and then you divide both sides by -1, you get your answer. And now we have the full solution. X is 3 and y is 6. Can anybody remember why I liked number 1 rather than the one I ended up picking, number 2? So it's almost a trivial reason, but why would I probably pick 1? Why would I probably pick 2? Got that back to front rather than 1.
Because you're adding in the second equation.
Yeah, I just know my own weaknesses, and I know when I rush, signs cause problems to me. And have you noticed how flexible this method is? Can't you use addition method to get rid of the x's or the y's? And it doesn't matter, both methods work. Once you got one half of the answer, can't you plug that into the first equation or the second equation? Actually, couldn't you also plug it into the original equation 1 or the original equation 2, and it would work then as well? So it doesn't actually, it's very forgiving, right? You can use, get rid of the x's, get rid of the y's. You can use a substitution, any equation that you've got, and they all work.
I have a question.
So that would be a, yes.
So I did I substituted to the second equation and I got y equals 2. But if you put that on the graph, would it be okay?
Well, let me do that version for you, because there is only one solution, so you shouldn't have got 2. So maybe if I go through the working for it, we might find out where you went wrong. So I'm going to substitute x equals 3 into this equation. Oops. 9x plus 6y equals 33, right? Okay, that way. So that's going to be 9 lots of 3 plus 6y equals 33.
I see what I did wrong.
Oh, I don't need to do it then, okay. You know that you can plug these two guys into Desmos and see where they cross, and that's a way of checking, but actually WebAssign will tell you you're wrong, so you know that's a quicker check, isn't it? So far, we really haven't done anything that new. That's kind of where we left off last time. So what I'm going to look at now is some of the more awkward versions of this question. So I'm going to start with the version of question 12. And we have 2y take away 3x equals -12. That's going to be equation 1. And we have 3x take away 18 equals 4y, and that's going to be equation 2. There's quite a lot wrong with this guy. Quite a lot wrong with this guy, number 12. The first thing is, it's not really written in a form that I can use the addition method. Have you noticed that in this second equation, the x's and y's are all over the place? They're not where they should be. Now, you can have y's and then x's if you like, that's fine. But if I'm going to have y's and x's, shouldn't I have y's and x's here? Right? And you always have numbers on the right-hand side, and those numbers have to be on their own. Not 4y, but a number here. So I'm going to take equation 2. taking this slowly. And what I'm going to do is I'm going to add 18 to both sides. I'm then going to subtract 4y from both sides. And that's the new version of equation 2. So one of the major issues that you're going to get for these last group of questions is that one or both of the original questions needs to be fixed, right? They need to be written as first variable plus or minus second variable equals a number. Now I can write the two equations with a fixed version. So it's going to be 2y, take away 3x is negative 12, and negative 4y, add 3x equals 18, and I'll call that 1 and 2. Those equations are at least got the variables in the right place, right? Everything's matching up. Do you notice anything nice about this question now that I've done that?
The x's cancel each other out.
Right, so actually, isn't this question going to be a lot easier to do because I don't need to fix, you know, times the first one by 2 and the second one by 3. I don't need to do that because as long as you've got the same number, but 1 plus and 1 minus, you can add. So these two added together is negative 2y. These two added together cancel each other out. And these two guys get you 6. So I'll now divide both sides by negative 2. And that gets me half the solution. Okay. Instead of using the word substitute, I'm just going to use put because it's smaller. What am I going to do with that guy? Well, I'm going to put him into this equation, yeah, or this equation, yep, or this equation, yep, or this one, yep, or even that one. And it doesn't matter one put. Every single one of them will work. Every single one of them will eventually tell me the x. So I'm picking, God, I don't know which one I'm picking. I'm picking this one because I want to. I don't think of any good reason. I just felt like picking it. So it's going to be 2 lots of negative 3, take away 3x is negative 12. Negative 6 minus 3x is negative 12. Add 6 to both sides. If you add 6 to that, you get negative 6. Right, negative 12 plus 6 is negative 6. And then if you divide both sides by negative 3, you got your second piece of the puzzle, and now we're finished. Are we comfortable with the adjustment that we had to make to this question? Because that one there wasn't really in the form that it needed to be. Are we comfortable about what we had to do there? Gotten some nods, so I feel good about that. It's one of the reasons I have videos. I can see your faces and it helps. So I'm now going to show you 2 different weird things in the same question. Right? 2 distinctly different weird things are going to happen. This is a version of question 15, but 16 and 17 are just like it. So when you get to do homework on these 3 questions, similar things to what I'm showing you are going to happen. So I've got 3x equals, I'm trying to find out what it is, equals 2y minus 8. And I have 6x equals 4y minus 8. Now, both these equations have y's on the right-hand side. They shouldn't be here. They should be over here where the x's are. So I'm going to take this equation here and subtract 2y from both sides. So you end up with this guy. And I'm going to take 4y away from both sides in equation 2. And I'm going to find that guy. Okay. That's a little bit better, right? X's and Y's, X's and Y's. I can't add these, it's not ready. Do I need to change one equation or do I need to change both? In this question here, could I get away with just changing one of the two equations?
Yes.
What do you think? Yeah. If I multiplied the first equation by -2, then I'd get -6x plus 4y equals 16. And if I leave equation 2 alone, we get that. Oh, this isn't good, but this happens. If you add these together, dead, no more x's. Oh, dead, no more y's, nothing left. On this side, you got 8. Now we talked last Wednesday, about this can happen, and it has a very specific meaning, doesn't it?
There's no solution.
0 equals 8, no solution. If you want to visualize it, it just means the lines are parallel. So our solution is that there is no solution. And that's actually what you type into the box in WebAssign. In fact, the one I'm looking like, it looks like you don't even leave a space, but I think you should. So no space solution. Wow. Can you imagine doing this and a slightly different answer appeared? 0 on the left again, but equals 0 on the right. That is a little bit different. How do you interpret that when it happens? How many solutions?
Infinite.
Infinite.
Yeah. So you will write infinite solutions. Are we okay with those weird things that can sometimes happen in the algebra? That all the variables disappear when you add. And you get 0 equals 10 or 0 equals 0. And 0 equals 10, or in this case 8, means no solution. And 0 equals 0, as it was in this pretend question, means infinite solutions. In a funny sort of a way, aren't these questions easier to do because there's a lot less work? I mean, once you add the two equations together, that's pretty much the end of the question. You don't have to do that and then put x equals 2 into this equation and solve for it. Are we good with that? Right. Now, I'm going to show you two special cases and how you tackle them. I'm not going to actually do the question all the way to the end. I just want you to be aware of how to solve these in case sometime in the future you see some more difficult versions. I'll do that again. Here's the first version. Okay. What's the problem here? Equation 1 has fractions in it. I think almost everybody, including me, do not like working with fractions. Do you agree? Fractions just cause problems. They make it hard to make the method work. Basically, you should avoid fractions like the plague. Unfortunately, the question may have fractions in them, right? Question 1 does. So what you need to do here is figure a workaround. So I'm going to take this equation and I'm just going to show you the workaround, right? How we fix it. If you don't like fractions, you make them go away. And you make that happen by multiplying all the terms by a special number. If you want to know what it's called, it's the LCM, lowest common multiple. I don't care. I like special number. Now, if I wanted to get rid of halves, wouldn't multiplying everything by 2 get rid of halves? And if I wanted to get rid of thirds, wouldn't multiplying everybody by 3 get rid of thirds, right? 2/3 times 3, the fraction goes away. If I want to get rid of 2 like halves and 3 like thirds, then the special number,
That'd be 6.
6. Yes, 6. So let's take each one of these guys and multiply them by 6. 6 times a half gets you 3. 6 times this guy gets you 2. 2 2s are 4. It gets you 4. And 6 times 3 is 18. There's your new equation 1. Here's your equation 2. Can you see how nice those two equations are to work with compared to the original? And I'm not solving that. You could solve that whenever you feel like it. But that's how you take care of linear equations that have fractions in them, right? Find a special number, in this case 6, that makes all of the fractions go away. That special number is called the lowest common multiple. A lot of people just know that if 2 times 3 is 6, and that'll work. Now, here's the last question, and then we move on to the next group of homework. Suppose one of our linear equations was this ugly guy. Now, I don't like working with fractions, and I don't think decimals are much better. So I need to figure a way of changing this equation into something a little bit easier to handle. And the technique is you multiply all the terms by 10 or 100. Typically. If I multiply all of these decimals by 10, won't the decimals disappear? 10 times this guy gets you 1. 10 times this guy gets you 3. And 10 times this guy gets you 17. So why do I need to sometimes do 100? Can you imagine the question was 0.12x plus 0.99y equals nothing 0.2 or something, right? So sometimes you have to multiply by 100 to make the decimals go away if the terms, the coefficients, are 2 decimal places. Now, once you've done that to it, right? Once you've got rid of the fractions or get rid of the decimals, you're here again, right? You're just back to normal equation, and you do it the usual way from that point onwards. Are we comfortable with those two and how you deal with those two special cases? How you deal with fractions, how you deal with decimals. And once they're dealt with, it's the usual question after that. Any questions about things that are happening in homework 4, solving equations? Do you feel good about what we've covered? Last chance. Okay, we're out of here. Let me move on, and where's the heck has that got to? Let's look on to homework 5. Here we go. forgot what number it was. And homework 5 is applications. Okay. Almost ready. I have to open up a window and then close another window, but I'll be ready shortly. Okay. And move it over, move it up. Oh, shooting space. Darn it, if I had a brain, it'd be dangerous. I opened up the wrong window after all that hard work. So I'll have to close that window and go back in and open the other window. So I think it was Bailey that was asking about this. We are almost ready. That looks good. Okay, everyone, not quite sure what I'm sharing. So now I'm going to show you what these questions look like. I guess you'd call them puzzle questions. Are we looking at homework 5? Is that what I'm showing you on the screen? Yeah, okay. There's 11 questions. I'm not quite sure what this is about and that is about, that whole thing here. I'm pretty sure all it means is go and look at some examples they've done. It will give you a clue on how to do them. And it's fine, but I wouldn't pay too much attention to it. So you're going to get a word story, and then you're going to try and solve something. So in question 1, a sporting goods salesperson sells 2 fishing reels and 5 rods, and the total cost was $260. And the next day, the salesperson, I'm going to shrink that out, you can't read it all. And on the next day, he sells 4 reels and 2 rods for $200. And the question is, how much does each thing cost? So how much does it cost to buy a reel? How much does it cost to buy a rod, right? So it's a word story, right? It's a puzzle. So let me take you through the steps that you typically should do in these kinds of word puzzle questions. A lot of people probably find these kinds of questions the hardest to do. It's a little bit easier when you're told what the things are and your job is just to solve it, right? That's what we've been doing so far. It's a little bit more difficult when you've got this extra layer where you have to create the equations that represent the story and then solve it, right? So if you keep that story in its head, I'm going to give you a very abbreviated version of it. On day 1, this person sells 2 reels and 5 rods, and it cost $260. And the next day, so on day 2, this person sells 4 reels and 2 rods, and that costs $200, right? So that's the question. So here is step 1. Choose X to be equal to the first unknown and Y to be the second unknown. I guess I could call them variables, but I chose not to. So in this story, there are 2 things that we need to find out. How much does a reel cost? So that's the first unknown. And how much does a rod cost? So I'm going to do X equals the cost of a reel. And then y is going to be the cost of a rod. So in the next puzzle, it might be how much does it cost for oranges and how much does it cost for apples? Or how old is Janice is the first unknown and how old is Peter the second unknown? Or how big's the first angle and how big's the second? Right? There's going to be two unknowns. That's step one done. Step two. Read the story. And create two equations using X and Y. Now, in the story that we got, on day one, it was 2 rods and 2 reels and 5 rods, and it cost 260. So that becomes 2x's plus 5y equals 260. Are you happy about how I got this equation from that sentence up there? Okay. Now on day 2, it was 4 rods, right? So 4 times x plus 2 rods, 2 times y, and that was equal to 200, and that's the second equation. And that's step 2 done. I think from the faces I can see, you still with me? You okay about how these stories became these equations? Okay. Right. Step 3. Solve the system of linear equations. By either using substitution method or addition method. And it doesn't matter which one of those two that you use, but you should only use those two. Do not use the graphing technique. The graphing technique's a little bit of a cheat, right? So we want you to do the math, right? So you have to do the addition or the substitution method. Both methods will work, but very often one of them, the way the equations are written, one of the methods is more obvious to use, right? Now, we didn't do so much substitution method, but see if one of these two equations said y equals x plus 22 or something like that, wouldn't that be a substitution method kind of look to it? But when the two equations are x's and y's jumbled up like this, typically the addition method is the better method to do. So at this point right now, we are basically solving a system of equations. So what do we have? A 2x plus 5y equals 260. I'll call that equation 1 again. And the other one is going to be 4x plus 2y equals 200. And that's the second equation. Okay, I've decided because of the x's and y's and the way this looks, that the addition method is the better method to use, right? So I've committed to doing that method. Would you agree I can't add them right now? I need to fix it. Any suggestions for how to change the equation so the addition method will work?
Multiply one of them by a negative number.
Okay, let's do that one. By what negative number do you want?
Let's do y.
Say again?
So 2.
2, I agree.
2y.
Oh, not the y, just the 2. Just the 2-bit.
Oh.
right? You always multiply, right? You're going to get something, but if you multiply this guy by -2, watch what happens to him. It becomes -4x, -10y equals -520. And if I leave the second equation alone, do my little wall. You see why that worked out really well? Can you see the x's killing each other off now? So when you do the addition method, can't you sometimes just change one equation? You don't need to change both. Do you know, if you're really, really lucky, won't you not even change either of them? You can add them right away, and it's great when that happens, but it doesn't happen very often. Could I have decided to get rid of the y's? Right. Now, if I did that, wouldn't this one have to be multiplied by, well, -2, and this one would have to be multiplied by +5, and that would change them both into 10s, 10y's, and that would work. So that might have been what Sarah was thinking of, and I just wasn't picking it up right. Are we good with that? Right, let's just finish it off. If you add these together, you get -8y. If you add these together, you get -320. You then divide both sides by -8, and you get 40. So that's half the solution. I'm now going to put y equals 40 into whatever equation my eyesight goes to. I'm going to go at that top one because that's where my eye went to. So it's going to be 2x plus 5 lots of 40 is 260. 2x plus 200. Subtract 200 from both sides and divide both sides by 2. That's step 3 finished. Okay. Y is 40, x is 30, right? That's step 3 finished. We've solved the equation, right? There is a fourth step. Answer the question. We were being asked in this question here to find the cost of a reel and the cost of a rod. So we should finish by saying cost of reel, and x is the reel, so that is $30, and cost of rod is $40. Why is that really even a step? Because you might say, well, it's pretty obvious. I'm not going to call them x and y when I'm finished. I'm going to call x the cost of the reel, and I'm going to call y the cost of the rod, and that's what maybe the sign would tell me. Sometimes they do this. They don't ask you to tell you what this is. They just ask you this. What is the difference in the price? Right, that might be the question. Typically, the last thing in the word puzzle is what you're being asked to find. And suppose the last thing in this one wasn't asking you to find the cost of them. The last thing is, what is the difference in price? What is the difference in price in this puzzle?
$10.
$10. And so there's only going to be one box, and you'll put $10 in it. So does that make sense that sometimes step 4 isn't what you think it's going to be? A lot of the time it will be, right? X and Y, the two things, great, write them down. Make sure you get them in the right place, because sometimes you put the 40 where the 30 should go and the 30 where the 40 should go, right? Sometimes you get them mixed up, and that's quite common. But in this case, it was a difference. Does this 4-step process have a structure to it that helps? Okay. Now, there's lots, and I think, well, not a huge number, but there's lots of examples here. So let's stop the sharing and let's go in and look at them and see what this tells us. Now, you might be scared when you look at question 2 because it's got funny things called ohms and you don't know what ohms are. And it talks about resistance and it talks about all kinds of things that look like it's electronics or physics, and that's not your thing. And then they give you a diagram, which is even scarier, right? And so what you can sometimes do is just get overwhelmed by it all. But let's show you that that question is really, in essence, a very straightforward puzzle. So I'll read it. 2 resistors in the voltage divider circuit in the illustration below have a total resistance of 1025. Right? To provide the required voltage, the first one, R1, must be 325 ohms greater than the second one, R2. Find both resistances. So right at the end, can you see the 2 things we're going to look for? A guy called R1 and a guy called R2, right? So that question's going to disappear, but imagine, all the information's there and you could always go back and look at it. I'm going to go through my steps here and see if we can make it happen. Put my little list over here, my shopping list. Step 1. I'm going to make X the voltage of R1, and I'm going to make Y the voltage of R2. Does that seem pretty straightforward that the 2 things we need are those 2 things, right? Do I care about the ohms? Not one bit. It's not going to change anything that I do. Now, it says read the story to get 2 equations. So I'll just read it out to you. The first piece of information says the total resistance was 1025. Now, the way I read total is that you added 2 things together and it came to 1025. Does that seem reasonable as my first equation then? The total resistance. Do I care what resistance is? No. All I saw was total of something, 1025. And the somethings are these, right? The somethings are always the X's and the Y's. Now, the next one says, to provide, the second equation now, to provide the required voltage R1, well, R1 is X, has to be equal to 325 greater than R2. So if you take R2 and you add 325, isn't that what that looks like mathematically? That this guy is 325 more than that guy. Does that make sense? Right. So the story that was in English, we ohms and diagram. Actually, couldn't they have made that diagram go away so it wouldn't distract the heck out of you? Could have just given you the written part and not even show you a picture. That's us. Once you get to here, it doesn't need to be a physics question. Isn't this now a math question? Let's move on to step 2. Look at the way these 2 equations are written. Do you think this is an addition method, or do you think this might work better as a substitution method?
Substitution.
I agreed. Haven't you got an X equals thing? Isn't that what substitution likes? X equals something or Y equals something. So let's do that then. So step 2 is solve it. So here we go. So I'm going to substitute. X equals Y plus 325. And I'm going to substitute it into this equation. So instead of X add Y, the X is going to be replaced by Y plus 325, right? So that's the X bit, plus a y equals 1025. Combine like terms, we get 2y's plus 325. Yeah, we're about halfway through this. What am I going to do to both sides?
Subtract by 325.
Can't argue with that. I believe that's 700. What are we going to do next?
Divide y, not y, 2.
Yeah. And we're halfway there, aren't we? Okay, let's find x then. Shouldn't you just substitute or put y equals 350? I like to do in a substitution method, I like this equation because it's pretty much ready to use then into this equation here. And so x is 350 plus 325, and that makes x equal to 675. And then we answer the question. And the question was the voltage of R1, which is what x is, 675. And the other one was the voltage of R2, and that's what y was representing. And that's 350. And if you want to write down ohms, go ahead. Are these questions a little bit less scary than they might have been when we started? Right? They have a thing, a process that you use. And typically, if you stick to the process, you will get there. We feel good? Any questions so far? I'm looking for, I see a few nods. Okay, let's go for it. This is question 4. Now, I'll just write down, it's a short one, so I can write it down pretty good. In a right-angled triangle, one acute angle is 21 degrees greater than 2 times the other angle. And the question we're being asked is find the difference between the angles. So there's your puzzle. Okay, I'll try my step 1. X is going to be the size of the first angle. I guess I could call it acute angle, but I don't think that helps any, so I'm not going to. And y is going to be the size of the second angle. Right? So you have to have an x and a y, and each story has 2 things, in this case, 2 angles. And x is going to be the size of the first one, and y is going to be the size of the second one, okay? That's my step 1. Now, it may be a little bit harder for you to come up with the 2 equations. One of them is relatively in your face, right? See this thing here, one acute angle is 21 degrees greater than 2 times. See that one there? That one translates into into an equation. Let's make it the first one. The first angle is 21 greater than 2 times the second angle. Do you see how I took this sentence and created an equation out of it, right? One angle, x, is 21 degrees greater than 2 times the other. Does that make sense? But there should be 2 equations, and right now I've only got one. And right now it looks like I've used up everything. There isn't anything else to get another equation from, but there is, but it's kind of hidden. And they went and said that it was a right angle triangle. And so can you imagine that this is angle 1 and this is angle 2? So I'm going to use a property of triangles, in particular right angled triangles. In a right angle triangle, don't 3 angles always add up to 180? In fact, that's true for every triangle. But if it's right angled, doesn't x add y add up to 90? Do you see where the second equation was hidden? It was hidden in the story that it was a right angled triangle. That was kind of sneaky, right? It wasn't obvious where that was. But I'd be comfortable that they too add up to 90 because the whole thing adds up to 180. And a 90 degree, which is what that guy is, that leaves 90 degrees for these two. And that's where this comes in. Okay, at this point here, I'm going to stop, except for one last question. Substitution or addition, what method do you think would work well for this system of equations? Substitution or addition?
Substitution.
Agreed. What made you go that road? Because you're right.
There's already an x equals 21 plus 2y.
You see that guy there? So substitution. Dot, 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 right? And then you finish it off in your own time. Are we comfortable about that question? It was a little bit sneaky about the x add y equals 90, but now it's done. I'll put that there for a second if you're still right. This one here is like 4, but question 5 is very like it. Question 6. Let's see what that guy looks like. In this puzzle, we're being asked to find out what x is and what y is. So x might be 20 degrees and y could be 40, right? Whatever it is. And all we're given to work with is essentially this picture. And x equals, when you get the answer, it's going to go in here. And y equals, when you get the answer, it's going to go in here. So let's see how my framework would work for this one. I think step 1 is really almost worth ignoring. isn't it obvious that X is going to be X and Y is going to be Y, because that's what they're called in the picture? So I don't really need a step one, right? I know I'm going to use X and Y, right? So I don't need to write down X is going to be X and Y is going to be Y, right? I tend to have that line when X is the age of Mary and Y is the age of John, right? Where there has to be some kind of conversion. Now, the tricky part is definitely coming up now. And this picture, everything we need to know is there, but we have to figure out how to get two equations out of this picture. You see this angle here that's 52? Did you know it's the same size as that one? It's called a Z shape. Did you ever, way back in the day when you did geometry, get told that when you take a triangle, when you take a parallelogram and you split it into two triangles, the two triangles are the same sizes, right? The same angles, but these are equal. So that makes equation 1, x take away 2y equals 52. And this one here is the same size as that one there. And so that's going to get me x add y equals 76. So if you never knew that property, you're probably not going to be able to do that question. Now that I've told you that property, haven't we now got two equations? Now, I guess what you might say is, well, what do I do if I come across something to do with geometry and I can't remember whatever it is? Well, you probably won't have to go and look at examples 8 to 11, objective 6. So in the book, there must be a question that is similar to this one that tells you that these angles are equal, and use it. Okay, I'm not going to take this any further, but when you look at these two, do you think this is going to be the addition method or the substitution method? Which one looks most likely on the information?
Addition.
Agreed. When you look at this question, do you want to get rid of the x's and y's? I think I might as well do that before I leave it. You want rid of the x's or do you want rid of the y's? Both work.
Wise.
Okay. Now, if you're going to get rid of the y's, then do you only need to change one equation to make that happen? And what will you multiply equation 2 by so that the addition method will work?
Positive 2.
Okay. Oops. Times 2. So you're going to leave the first equation alone. And you're going to multiply everybody by 2. So on what? 152. And would you agree that that's pretty much ready to go? Can you add them and get the x's, and then once you get the x's, you can figure out the y's, and boom, you're finished. So I'm not doing the rest. You don't need to do the rest right now. You can do it in your own time. WebAssign changes numbers. So when you do your WebAssign, that won't be 52 and 76. That'll be 81 and 33 or something, right? There'll be different values. And so this is just the process, not the specific question. Okay, let's pause at this moment. Is there any questions so far? Are we okay with these puzzle stories, these word puzzles? Got a good nod? Sarah, oh, thumbs up, perfect. I'll take thumbs up. Thumbs up are good. What's the next one? Okay, this one I'm about to do is 7 and 8 are like this one. And you've got that iconic picture. Oh, let's show you it. It's a bit of American history. I would think almost, I hope, I'm not sure if hope's the right word, but I would expect everybody, can you remember that? It's on stamps and there's statues in Washington and all sorts of things, right? The raising of the flag, right? And it's in the Arlington, Virginia. My apologies, I thought it was in Washington. And in this picture, there is an angle that the flagpole is going. And that angle takes the horizontal line and it splits it into a guy called angle 1 and another guy called angle 2. Right. Now, I'm now going to go back into the whiteboard and see what we've got to work with this time. So I'm going to have a step 1. I'm going to make x equal to angle 1. And I'm going to make y angle 2. And now I'm going to get 2 equations. Now, I'm reading this out loud, so one of the angles is 21 degrees less than twice the other. So I'm writing this down in English. One angle is 21 degrees less than twice the other. That has to turn into an equation using x's and y's. So let's say the x angle is 21 degrees less than twice the other. How do you write 21 less than twice the y's?
21 minus
Well,
2y.
Oh, good. You'd said it before I started writing it. There is another possibility. But that's not right. Twice the angle, take away 21 is the right version. Can you see why this is back to front? Right, so, okay, I'll call it equation 1. That's the end of the story. We need to find a second equation with x's and y's. Now, if I call this guy x and I call this guy y, do you notice anything in the picture that's going to be the clue to getting the second equation?
The straight line.
And how many degrees is a straight line?
180.
So there's your second equation. Do you see it's hidden? Right. They don't like shout it at you. It's just kind of subtle. It's there, but they don't even push it. So you have to look really hard to find it. But would you agree, straight line 180, x add y 180. Right. Straight line 180, x add y 180. In this case, would you agree substitution is the way to go? Are we good with that question? Do I need to look at nodes again? Okay. Okay, I'm just going through. I guess I'll have to show you this one. I'm going to look at question 9 now. As you go through these, they get harder and harder, right? This is question 9. I believe, is it 13? It's 11, 13. Oh, 11, okay. So we're done close to the end of these guys. It's all right, there are only a few more to go. Use a system of 2 linear equations to solve these? Well, that's how you solve all of them, so I'm not going to, that's not telling me anything I don't know. A sales clerk can choose from 2 salary options: a straight 10% commission or 350 plus 5% commission. And the question is, how much would the clerk have to sell for each plan to produce the same monthly paycheck? So you can, I mean, there are some places where your wages are all commission, right? If you don't sell a thing, you don't get nothing, right? And if you sell a lot, you make a lot. But most places are kind of combination of, you know, $400 and then 4% commission, whatever it might be. So we have to figure out how to convert that into the solution. The question here is not directly anyway a question that, how would I say this right? It's not obvious looking at this question what the 2 equations are going to look like, nor is it that obvious what the X and the Y are, for that matter, right? So I'm just going to write down the gist of it. You can get a 10% commission, or you can get $350 plus the 5% commission. And we want to know, what do you need to sell to make the same amount? Okay. This is going to be a little bit sneaky. X is going to be the amount you sell. And Y is going to be how much your wages would be. Okay, so that wasn't obvious who I'm going to make X and who I'm going to make Y, but I'm going to go X is the amount you sell, right? And Y is your wages. So far, so good. Now, if you get a 10% commission, won't your wages be 10%, which as a decimal is 0.1x? Are you happy about 10% commission being your salary Y is 0.1 times what you sell? 10%. Is that okay? Are we good with that? Right. Now, the second one is your wages are 350 plus 5%. Are you happy about the second equation now? Your wages are $350 plus 5% of what you sell. So there's step 1. And this is the beginning of step 2. Okay, let's go hunting. Would you agree that this is a substitution method question? Why? Because I have a Y equals here. Could I turn them into whole numbers? I could, but I don't think it's worth it. So I'm going to solve this system of equations, these 2 equations, using substitution. So I'm going to substitute Y equals 0.1x into Y equals 350 plus 0.05x. Let's see what happens when we do that then. Nothing 0.1x goes here. And it's going to be 350 plus this guy. Now I know these are ugly decimals, but I think we can fight with this, right? We can survive with this. Yeah, as long as you do it to both sides, it's okay, rule. What should I do to both sides here? Okay, if that was 2x and that was 3x, what would you do then? Wouldn't you subtract 3x from both sides? Right. Okay, let's just subtract 0.05x from both sides. If you subtract it from 0.1, you're still left with 0.05x, and it's equal to 350. Just think what you would have done if it was, I don't know, 12x is 350, take away 2x. Wouldn't you, or add, right? Wouldn't you take away 2x from both sides? Right, ugly decimal doesn't change the method. Don't you still take that guy away from both sides? And if you go to your calculator and you do 0.1, take away that guy, this is how many is left. Again, it's ugly numbers, but forget the numbers. What do you do to both sides to get x?
Divide.
And don't you divide it by that ugly looking guy? So I'm going to take 350. I'm going to divide it by 0.05, but that's what calculators are for. So 350 divided by 0.05, and I get the answer 7,000. Are we cool with it? Now, if I wanted to find y, wouldn't I just go up here and plug 0.1 times 7,000, and I can do that in my head, it's 700. Or I could plug it in here and it wouldn't matter, I'd still get 700. But the question went and asked us, how much would he need to sell? So that's the only answer they want to know about. If the question had been, how much does he need to sell so that they're both the same? It's 7,000. If they wanted to know how much money would he make that month, it would be 700. Are we okay with that one? I think we need a joke before we do the next one, because poor Rachel's brain is beginning to turn into sponge, isn't it, Rachel? You need a break. I need one as well. Right, so let's have a break and do a joke. Anybody got a joke for me? No jokes? Well, you know I'm going to tell you one. Do you want to hear
I got
mine?
a joke. Oh, sorry.
Oh, great. Go for it.
My sister just told me this one. She says, what's the difference between a dirty bus stop and a... Okay, actually, I have to have a moment to remember it. Somebody can go before me.
Okay. Okay, while she's doing this one, I'm going to tell you a joke, but maybe someone else has got another one before I do it. Okay. If you are an American before you go into the bathroom, and you're an American after you come back out of the bathroom, what are you when you're in the bathroom? Don't know? European. Nothing? Oh, good. Francis enjoyed it. At least one of you thought it was fun. Dawn, was that bad it was good, or was it just bad? Yeah, okay, that's a thumbs up. I'll take it. Lexi, have you got your joke now?
Yeah, I do. My sister, she always says,
Okay,
what's the difference? What's the difference between a dirty bus stop and a lobster with breast implants? One is a crusty
I
bus
have
station.
no idea.
Yeah, one's a crusty bus station. The other one's a busty crustacean.
Oh, Corona. Oh. Yeah, that's
Yeah,
a hard
it's
one to
awful.
remember.
It's awful,
I
I
can
know.
understand that one. Oh, but I don't mind awful. I like awful. Awful is good. Francis, he's got his thumbs up. He likes everything. That's great. Or she likes it. Okay, remember. Right, now, I want to tell you, it's not really a joke, it's a true story. Do you see behind my head? I'm trying to move my head out the way. I'm not sure which direction and go this way. Yeah, this way, right. Do you see that castle in the background? It's my background for today. Can I make that bigger? That would be interesting if I could. Hello, can I make this bigger? Nope. What about that? There we go. Are you just looking at me in the castle now? Which is a scary thought, but is that what you're saying? Nope. Is it still a little picture or is it a big picture?
It's the same.
It's the same. Okay. Well, use your imagination. I am going to show you what is going on here. This is one of my favorite castles. It's Edinburgh Castle. And it's on a big lump of rock. And below the rock is Princess Gardens. And the castle is up here. Not a very good artist. And I have been literally to this castle about 100 times in my life. Every time I go to Scotland, I go there. But when we were young, it was like it took us about an hour to get there, and we used to go there a lot when we were young. And it was just one of those places that you never get tired of, because there was always something you found that you didn't see the time before. It's got a museum in it, and it's got all sorts of cool stuff. So we went on a tour once, and what you might notice is that on these castles, although you can't see it on this thing, there is very often a bit that sticks out that looks something like that. So it's like a buttress, right? It sticks out. And I just thought it was architectural, you know, because they do that in castles. But actually, it's a toilet. And castles were, you know, the kings lived in castles, right? So they get the best of everything. And you got to talk about before plumbing, right? There was no plumbing, right? You know, plumbing is relatively new in the scheme of things. And toilets in Edinburgh, which is from here, there's a road leading down, and that's called the Royal Mile. Right, it's a road that goes that way. And along that, they've got houses. And in the old medieval days, you did your toilet in a bucket. And then you opened the window and you chucked it out into the street. That's sewerage removal. But they had 2 times of the day you're allowed to do it. So it wasn't like you did it all the time. And one was early in the morning and one was late at night. And all that they basically did is they waited for it to rain and then gravity took over. But the people in the castle, they got a toilet. And the toilet ended up being a wooden seat with a hole in it. And here, there's a hole. So the queen or king would sit on it and they would poop and it would just shoot down the side of the castle wall. And that was thought to be the height of luxury. You could go and poop anytime you liked and it never stayed in the building, right? It got, whoop, gravity, gone. And I was curious because I was quite young when I went for this tour and I used to ask all sorts of questions. So the person that was giving us the tour, I went and said, what happened to the poop? Does it just lie there? I mean, does it wash away eventually? And she says, no, what they'd done is that they had a whole load of pigs that they kept right at the bottom. And if you know anything about pigs, they'll eat anything. And that's how the sewerage was taken care of. The pigs ate it all, or most of it. So I then went and asked, and I shouldn't have, the next question. And I asked them, what happened to all the pigs? Well, they used to take some of them, roast them, and eat them. And is it any wonder why the average age of anybody in Middle Ages was about 35? Can you see how many ways there were to die? Right? So there is a useless piece of information about toilets. You never knew you were going to get that lesson today. Medieval toilets are a hole in the castle that you poop through. And running water and plumbing did more to increase the life expectancy of everybody than almost any other leap forward in advancements, even in medicine. Are we now ready for the last couple of questions on this, and then we can start a new topic? Do you want to go to Edinburgh Castle one day and see that? Some of you are thinking, no way am I going to look at a medieval toilet now that I know what they were like. Okay, let's move on then. Where are we? Well, question 10 is a video. You watch it and answer the question, so I'm not going to do that. And so we come to our final one, which is question 11. Oops. Let's show you the question first. And I've lost the damn thing. Here it is. So it is in two parts. Suppose you and a friend are on a vacation and you decide to paddle a canoe to the other side of the lake. You keep track of the time it takes you to travel across the lake and then back home. Okay, you can't see me doing this, but I'm drawing a lake. And I'm going here. I'm drawing a little dotted line to the other side of the lake. Gotcha. And I got a little picture of that, right? The wind is blowing across the lake so that the current of water helps you to travel faster across the lake on the way back. So I'm drawing a little picture with an arrow and I'm putting the word wind on it. Like that. And now I'm lost. Oh, that's what's going on. Okay. The distance across the lake is so many hours. The trip out across the lake takes a certain number of hours, and the trip back home takes so many hours. Okay. This is a very interesting question. I'm writing it down right now. Okay, we got it. So being the last question, they are allowed to do anything they like, and they've decided to go weird on us. Here's my story, kind of visual. Here's the lake. Well, I guess the good news and the bad news is that whatever you type in here is what you want. So how big in miles do you want the lake to be? So it's really any number you like. That's what's unusual about this. So in my case, how wide do you want the lake to be? Don't pick 20,000 miles, please, but give me a number.
1.
Oh, too small. Come on, give me a
5.
number that I can work with. 5, okay, I can work with 5. So it's 5 miles. Gotcha. Now, we're going to put in how long it took to go this way and then how long to come back. And remember, coming back is going to be less than going forward, right? So I'm going to say, when you went this way, it took 2 hours. But when you came back, it only took 1 hour. And I made those numbers up. And I guess I put hours in 2 places, but never mind. I have created my own question. That's what's unusual about this. Now you can create your own question. You can make this 1 mile if you feel like it. Make that 7 hours and make that 4 hours. But remember, this has to be less than that because of the story, right? It was quicker coming back than it was going. Now, from all of that information, we have to create an equation. And we are clicking on the next fella. I'm going to, well, I normally use X's and Y's, but not this time because they're making me use other letters. So S is going to be the speed that you can paddle. And C is going to be the speed of the wind, I guess. Guess you could call it the current you want. And we are going to create 2 equations using this information. Now, we know that the distance is speed times time. Have you ever seen that little guy? Rate times time? Yes, no?
Yep.
Okay. Right, now, R is basically your speed. So I know from this story here that it's 5 miles and this one takes 2 hours. If I rearrange this, then I can create any equation I like, but I'm going to use 5 miles is equal to the speed I paddle times 2 hours. And that's my equation 1. And 5 miles is speed plus current times 1 hour. And that's my equation 2. Solve for S and C and you are finished. So if you want to write that down, 5 is 2S and 5 is S plus C. And when you do that, you will be able to get the speed of the current and the speed of the canoe. So that's the speed of the current C, and the speed you paddle it, I guess they're calling that the speed of the canoe. So once you find S and C, question's over.
Can you?
I'm looking at that. That question looks very easy, isn't it? Looks very easy. I wonder if it is. That is us finished the word puzzles. The last one was weird in all sorts of ways. We're now going to start, because we have at least another 35 minutes, we are going to start our next section. If you can bear with me for a minute.
Oh, shoot, sorry.
Yes. I hear something, but not a question. Okay. Have we got a question? Last chance. Are we good then? Okay. I'm zooming about here with lots of windows because we've got far too many open. And I'm going to go up here and just do that again. That's much better. I can see you all. Our next homework topic. This is homework, I think it's 6. This one called. Homework 6 is going to be rational expressions and functions. And I'm going to do the intro to it today. I'm not going to do any of the homework questions because there's a lot that we kind of need to be reminded of before we go here. So let me show you what a rational expression is. Is an expression that takes the form of a fraction. So a rational is just an old name for a fraction. So we could have called these fraction expressions. And homework 6 is going to deal with simplifying them. So if I gave you the fraction 4/6, would we all feel comfortable that 2/3 is its simplified version, right? You can't make it any simpler than 2/3. So numbers are not difficult things, but that technically is a rational expression. It just happens to have numbers. We are going to be solving or simplifying much more complicated things. We are going to be simplifying things that look like this. And when we are talking about rational expressions, this is the kind of thing we're really talking about. This horrible thing can be made simpler, right? It can be simplified. But it requires a fair amount of algebra, and it also requires that we are good at factoring, because that's going to be our major way of tackling these questions. So that's what we're going to focus on today, how to factor expressions. And once we're good at factoring, we'll then, when I see you on Wednesday, we'll work on these types of questions. So let's start with what are called common factors. So if you had something like 4x plus 10y, a common factor would be, in this particular question, would be 2. Are we comfortable with common factors? How you find the biggest number that works with 4 and 10, in this case 2, and that has a name. That 2 is called the common factor. Can you remember doing that way back in the day somewhere? Common factors. Right, let's up the ante to something much more complicated. Now, in this expression, we're going to also pull out a common factor, but there are going to be a number of common factors, right? There's more than one thing that's common to both pieces. Would you agree 2 is a common factor?
Yeah.
Right, I have an x squared and I also have an x cubed. But which one of those 2 is the common factor? Because there's a rule about which one you use.
6.
X squared or X cubed? Which is the common factor?
X squared?
Yes, you always pick the smaller of the two choices, right? So if you've got an X squared and an X4, you pick X squared, right? If you have an X cubed and an X, you pick the X squared. We have a Y and a Y squared. What's their common factor going to be when it's a Y and a Y squared?
Just the Y?
Just the Y. Isn't it the rule, the smaller of the two again? So when you're looking at common factors and both of them have an X or some version of X or some version of Y, what you need to do is, okay, this one's got that guy and this has got the other. The smaller of the two is the common factor. Now, that's the first part. You identify the common factor. In this case, there's 3 of them. So I guess I should call them common factors. But the second piece of the puzzle can sometimes be just as awkward. If you pull out 2x squared y as a common factor, you leave behind some things, right? There are bits left over. I'm going to ignore this bit for a minute and look at what is left over here. There's going to be a negative. 2 into 8 gets me 4. If you take an x squared out of an x cubed, aren't you left with an x? And if you take a y out of a y squared, you're left with a y. Are you happy about this leaves behind that? Can you see how I got this? Right? 2 into 8, x squared, used up 2 of them, y used up 1 of them. That's what's left. What sometimes people get a little bit confused about is what goes here at the beginning. Because the 2, in this case, the x squared and the y, were all used up in the common factor. And a lot of people think that means you leave it blank or write nothing at all. But that's not actually the case. You do put a number here. What number do you put if you use up everything in the common factor?
1.
You put in a 1. Now, if I've done this correctly, shouldn't I be able to distribute this and get back to here? And do you see why the y1 is important? Because 2x squared y times 1 gets you this guy. And if you multiply 2x squared y by this, trust me, you get that. So that is a common factor. Do you want to see another common factor, or are you comfortable with common factors?
Can we do one more?
Sure. Let's do 15 x a squared b cubed take away 3 x cubed a b to the 10. That's probably more difficult than you're going to see, but might as well do it. Right. There's a 3 and a 15. What number is the common factor when there's a 3 and a 15?
3.
3, great. There's an x cubed and an x. What's the common factor now?
X.
There's an a and an a squared. What's the common factor now?
A.
And last, there's a b to the power of 10 and a b cubed. What's the common factor now?
B cubed.
Right. Are we happy about how we found all the common factors? Does that make sense where we got them from? Okay. Now, let's see what's left. That can be a bit of a challenge sometimes. Right, 3 and 15, right? 3 is a common factor, but we should have 15. So what do I need to fill in to make it up?
5.
Agreed. X and X, oh, used up. A and A squared, right? A is a common factor, A squared is what we want. What do we fill it in with then?
An A.
Just an A. This one's a bit sneakier. B to the 10, B cubed, right? So B cubed is a common factor, right?
So B to the 7th.
What do you fill in? Well, Here, yes, but we're talking about the first time. I shouldn't have put my fingers near that. Right, we're still doing the first time. So what do you get when you take out a b cubed out of b cubed? Nothing, right? It's used up. So 5a is this term. Let's check it. 3, 5, 15. Agreed. X used up. A left over. B cubed used up, right? That works. Now, take away. That b to the 7 you said is coming in right now. 3 used up, so don't write anything. X and x cubed, right? Common factor of x, x cubed. What are we going to have left over then?
X squared.
Okay. An A and an A, doesn't that just all used up? A B cubed, this is your 7 then. Right? A B cubed and a B10. You see that one? That's where the 7 goes. And that's, as I said, that's probably more difficult than you're likely ever going to see in this section. But if you can do that one, you can do everyone in the everyone you're ever likely to see, right? Because that's ridiculously ugly. And that's examples of what are called common factors. I call these guys, we're going to factor them. These are called difference of two squares. I think that's what you Americans call it. You call them difference of squares, or do you say difference of two squares? Can't remember. Difference of two squares or just difference of squares? Don't matter. X squared take away 25 can be factored. It's a difference of two squares. So if you ever see two terms subtracted and each term looks like it's something that's being squared. So you can see in this case it's an x squared and a 25, right? Something being squared. Then you're probably looking at this situation called a difference of two squares. And when you have that, this is what the factors look like. You get x plus 5 and you get x take away 5. Can you remember that algebra from somewhere, right? Who knows when you did it, but it's a while, right? Now, how about a squared take away b squared? That is also a difference of two squares. I'll take a volunteer. What does that factor out as?
A minus B in the first one, and then A plus B.
Yeah, I put the pluses first, but that's totally cosmetic. If you like A minus B times A plus B, feel totally free to do it that way. It's exactly the same thing. I don't know why this one causes trouble, but it does. That is a difference of two squares.
50 minus C, then 50 plus C.
It's exactly the problem it causes. And I'm not quite sure where that comes from. And it's okay, because you're not the only one who do that mistake. It's not 50 plus C and 50 takeaway C. You're okay with the plus C and the takeaway C, by the way.
10
It's
times
the number
10.
that you used.
Oh, duh.
Yes. But it's something about 100 that makes that question so common. That is exactly the kind of mistake I see people making. I don't know, is it just 100 is kind of nice and round, so you kind of go 50-50 because you're thinking half, not square roots?
It's just a good trick question.
Just be aware. Yeah, you just, it happens. God, I'm probably going to do it sometime in the next 9 weeks. I'm going to do some just as obvious as that. Okay, are we cool with that guy? Here's another one that causes problems for a different reason.
It's just one because 1 times 1 is just 1.
Yeah. But didn't you have to think about it or convince yourself you were right before you committed? Because it kind of just looks wrong, doesn't it? And, well, for some
Yeah.
people, it looks wrong.
Wouldn't some people it would be like 1 times 0?
Oh, God, I hope not. Because it'd be wrong, but they could, you're right. They could go some other place, but that's what it is. Are we good with difference of 2 squares? Do we feel comfortable about something squared, take away something squared, and sometimes they're numbers and sometimes they're variables, but that's essentially what they look like. We feel comfortable with them, right? And thank you, Rachel, for doing that mistake, because you helped a lot of people. Because a lot of people were going to do the same mistake, and that made me say, hey guys, fix it, don't do that. And I can guarantee that you will never do that one again. Agreed?
Nope.
See? But that's what learning is, right? Making a mistake and then not doing it, right? Picking a really dumb, stupid boyfriend and dumping him, right? You're not picking that boyfriend again, right? That kind of decision that you make in life is sometimes some of the most useful. As all people are, including me, I was really dumb when I was young, but I got really lucky, and one of the best decisions in my life was marrying my wife. Anybody who can suffer me and still be married to me for this length of time deserves a medal. Can you imagine how awkward I must be to live with? I'm a scatterbrain. I tell really bad jokes, whether you want to know them or not, right? I tell you useless pieces of information about toilets in Scotland, whether you wanted to hear them or not. My poor wife has had to suffer that for years. And she still likes me. Go figure. I got lucky. Okay. C. Quadratics. Simple version first. Quadratics are also called trinomials. Maybe you've heard that term instead. So we're going to factor simple quadratics, right? Simple trinomials. Right. Show you an example of that. Trinomial is quite a good name, isn't tri meaning 3, like a tricycle has 3 wheels? So a trinomial has 3 terms. A difference of 2 squares only has 2, but a quadratic or a trinomial has 3. So it's easy to tell, I think it's easy to tell the difference, right? You shouldn't mix these guys up with these ones. Now, trinomials factor as 2 guys multiplied together, a bit like this. But there are rules when it's simple. And the rules hinge around this number here. And in English, what you're looking for are 2 numbers good grief. Yeah. 2 numbers that multiply together to give -8. But when you add these 2 numbers, you get whatever that guy is, -7. So you're going to have an x here and an x here because x squareds give you x's. Right. Two numbers that multiply together give you -8, but when you add them, you get -7. If you can find out who those two numbers are, you put one number here and the other there and you're done. So who are the two guys at work for this question? And you might be saying something,
Negative
Bailey, but I
8 and
can't hear it.
1.
Oh, well done. I got a -8 and a +1.
Negative 8 and 1.
Agreed? That's what Sarah said. Agreed. Hey, who are you nodding at? Is your husband joining in saying, yep, you're right?
Yes,
Okay.
he did.
Hey, tell him if he is listening to this lesson, I'm charging him $14 an hour because I need money. Only joking. Right. Let's double check that she's right. Would you agree that these two multiplied together give me -8? And that if you add these together, don't you get -7? And that is the correct factoring. I'm not going to get into it today, but when we see you on Wednesday, I'll talk about foiling. And foiling is when you multiply this out. And sometimes what you have to do is foil it out just to double check that you're right. But can you just trust me that this is correct, right? So let's try another one. X squared plus 6x plus 8. Two numbers that multiply together give you +8, but when you add them, you get 6.
4 and 2.
Agreed. A rule about these numbers. You're not going to get questions where it's some ugly fraction and another one, right? It's not going to be 8/17 and 411 fourths, right? It's not going to be weird things. The numbers that you get are always whole numbers, right? Or at least integers, right? +2 and -7, +3 and -8. It's never going to be -1/2 and a +8, right? It's never going to be combinations with fractions in it. So when you're going through all the ways to get 8, just go 1 and 8, 2 and 4, right? And play about with those because they're the only ones that are really going to be of any use to you. Okay, you're getting good at this. Let's put you under pressure. Probably bigger than you're ever likely to deal with, but you know, big numbers can happen. Oh, God, Himmel. Sorry. Let's make the question possible. Plus 10x minus 120. Almost gave you an impossible question there. I'm getting tired. There. Two numbers give you 1200, -1200. One's plus and the other's negative, right? When you add those two numbers together, you get +10.
Uh, 10
Any
and
ideas?
12.
Well, 10 and 12s would get you, what, 22? Wouldn't really, I mean, it works, but it's not the right one. I mean, it works for one piece, but not for the other.
Isn't it 120?
You know it's going to be well, it's 1200, so it's 1200. Last chance. Anybody got it? +40 and -30. If you multiply them together, don't you get -1200? And if you add 40 and -30, don't you get +10? Okay. I am going to give you 4 questions to do. And You're only getting 5 minutes. So your goal is to get as many of the 4 done as you can. Be a miracle if you get them all done. And I've decided to use different letters so we don't get caught up with X's all the time. Oops, sorry, that's a Y. There's your first one. You can work on that while I figure out what the next one's going to be. There you go. No pressure, 5 minutes. Go for it. Okay, we're inside our last 1 minute now. Okay. Let's go different volunteers each time. Spread the wealth. Any volunteers for question 1? What combination multiplies to give you -50, but adds together to give you +5?
I know.
Go for it.
+10, x
Right, Bailey?
10,
Huh.
and x -5.
Hope you all agree with that one. That's the one that works.
Yep.
Okay. Somebody different. What combination works on this one? It says y² take away 5y - 14. So
I
two
put-
numbers multiplied together give you -14, but when you add them, you get -5. What'd you get?
I put y in
Rachel.
-7 and then y +2.
Let's check it out, because she's right. You see the -14 when you multiply them? You see the -5 when you add them. Okay. Bit harder as you move on, because not all of you got to the third one, but some of you hopefully did. I'll take a volunteer for the third one. How's
I
this one
put-
going to work?
I put b -1 and b +2.
That looks good to me. Would you agree? Multiply them, you get -2, but when you add them, you get +1. Did anybody get to the last one?
I
I
put-
got
Oh, go ahead.
b
Oh, is it?
+2
Say again.
and
Correct.
c
Savannah?
+5.
You nailed it. You all agree on that last one? Those who got it?
Yep.
So what is going to happen tomorrow, Wednesday? Phew, give us a break, right? What's going to happen on Wednesday is that I want to look at factoring complicated trinomials. Now, what's the difference between them and the one that we've done? It won't be x² anymore. It'll be 2x² or 3x². And that little change makes a big difference to the factoring, right? It becomes much more complicated to get the right factor. We'll also, on Wednesday, look at FOIL, just so that you can use that to check that you've done it correctly, because sometimes you might not know that you're wrong, and if you FOIL it out, you'll find out that you're wrong. Hopefully not too often, but it's worth a check. And then once that's happened, we can then start on how to simplify fractions. And the technique's dead easy. You factor everything in the top, right? That's why we're doing all this. You factor everything in the bottom, and then, with a bit of luck, something on the top will be the same as something on the bottom, and you cancel them out. And then whatever's left is your simplified answer. So that's basically how the strategy